Hello everyone. The topic of my presentation is gamma irradiation modified metal nanoparticles with enhanced chemical properties. Um, Actually, gamma irradiation can be used in two different ways. Firstly, to use an external source of irradiation, and the second is to use an in situ radiation, wherein you can use a radioactive isotope of the sample inside in your solution and use that radiation to produce the gamma irradiation, to produce the nanoparticles. And in external source of radiation, you just put in your sample in a chamber of gamma radiation and irradiate the solution externally to produce the nanoparticles. Now, firstly, we chose gold nanoparticles because they are very easily prepared, and many people have reported the formation of gold nanoparticles, and they have been investigated for use in sensors for both chemical and biological warfare agents. Nanoparticles of gold can act as tiny, precise, and powerful heaters, which potentially could be used in biomedical applications. By using biolinkers, the nanoparticles can be designed to affect specific targets such as tumor cells. So, we produced radioactive gold nanoparticles using neutron activated gold, that is 198 radioisotope of gold. We took an auric chloride salt solution and spiked this radioactive gold salt to stable gold salt solution and added to polyethylene glycol 4000 solution and allowed to settle for some time. Then the color changed to beautiful magenta color, and then we just analyzed it for gamma spectrometric studies to see whether it has decayed or not, and then we took it for UV visible measurements and transmission electron microscopic analysis. We could observe the surface plasmon resonance characteristic peak at 560 nanometers, and 10 images indicated that there were 20 to 30 sized nanometer sized 20 to 30 nanometer sized gold particles, in contrast to the very large size in the presence of stable gold. So it was evident that radiations converted the gold to nanoparticles, and the reason was that gamma radiations caused radiolysis in the solution, causing hydrated electrons and hydrogen and hydroxyl free radicals, which propagated through the polymer chain of polyethylene glycol and finally reduced the cationic gold to gold zero, which agglomerated into gold nanoparticles. So at that time, this was about in 2006, and at that time it was very exciting as we could find that 198 gold is short lived with half life of 2.69 days and has high intensity gamma energy at 411 keV. Thus, radioactive gold nanoparticles may be useful for in vivo and in vitro applications where both the properties of nanoparticles as well as high energy gamma ray will be useful. So we extended our studies to see whether this generation of nanoparticle could be done in biological cells also, and we selected the yeast cells of Saccharomyces cerevisiae, and we just put some live cells of yeast in auric chloride solution and kept it for 15 minutes, and we could see that gold nanoparticles were generated even within 15 minutes inside the cells, and the particles grew more after 1 hour, and there were more number of particles after 24 hour. Even the size also increased after 24 hour. After 48 hours there were more number of particles, and after 72 hours there were even more number of particles with larger size, and we could see that the particles aggregated inside the nucleolus of the cell, in contrast to the stable gold solution which migrated inside the cell but did not form the nanoparticles. So the radiation caused radiolysis inside the cells, and which finally produced free radicals, and the nanoparticles were generated. And this picture shows the budding yeast, which shows that the nanoparticles are not transmitted to the next generation. So, our next motto was to see whether external radiations could also produce changes in the properties of the nanoparticles, where it can be used for some other analytical purposes or not. So, we used peanut skin polyphenols to mediate the synthesis of iron oxide nanoparticles and use it as an anion sensor for perchlorate ion. So first we synthesize the nanoparticles and characterize them, and also produce the nanoparticles in presence of low dose gamma irradiation with a dose rate of 2.9 kg per hour, and studied the spectral sensing of perchlorate. Now, polyphenols are available in different food items, and they are reactive species towards oxidation. Many people have reported production of metal nanoparticles like copper, silver, iron, nickel, zinc, and so on nanoparticles in presence of food polyphenols, and they have different properties like antioxidant activity, anti-cancer activity, UV protection, antimicrobial, and so on. We have chosen peanut skin because we thought that peanut skin would be best out of waste, and the biomaterial, it is easily available, cost effective. Aqueous extract is a rich source of polyphenols and is a good reducing and stabilizing agent during nanobiosynthesis. The reported presence of different polyphenols in the peanut skin extract are these. And iron oxide nanoparticles have separate applications in different fields like catalyst, magnetic data storage, semiconductor, MRI, wastewater treatment, and so on. So we synthesized our nanoparticles by taking 2 gram of peanut skin in 100 ml distilled water. We soaked it overnight and adjusted the pH to 3, and added 1 ml of 5 molar ferric nitrate to 5 ml of the peanut skin extract, and the color changed from yellow to brown to green to black, and we called it set A. Similarly, we prepared a set B, which we kept inside a gamma chamber for 15 minutes, and another we prepared set C, which we prepared by keeping the solution in the gamma chamber for 24 hours. Now we characterized by taking the absorption spectrum, which showed the characteristic surface plasmon resonance at 430 nanometer. With increasing concentration of iron, it showed increasing absorbance at 430. The TEM images showed nanoparticles with size 30 to 50 nanometers. The powder XRD pattern showed that the particles are amorphous, which is really very good, because amorphous iron oxide nanoparticles are difficult to prepare, and they have very interesting surface properties. The Raman spectral pattern showed that the particles are of alpha iron oxide type. The infrared spectral properties showed that there were the presence of iron oxide, which means that the polyphenols formed complex with iron, and the iron oxide stretching could be found in the range 530 to 670 centimeter inverse. And these peaks were found in both in all the sets A, B, and C. Now, for perchlorates are present in the nature because they can be obtained in solid propellants of rockets and missiles, fireworks, road flares, blasting agents, automobile airbags. And perchlorates resemble very closely to the iodide ions. They reduce thyroid hormone production in the thyroid gland, and some studies have suggested that perchlorate has pulmonary toxic effects. Now, for sensing, we have taken 2.2 milligrams of the iron oxide nanoparticles, and they were taken in 2 ml of different salt solutions of different anions and soaked for 1 hour. The supernatant was then analyzed for the spectral modifications, and we can see that at near about 300 nanometer, uh, none of the anions showed any response, but perchlorate showed a very high peak, and the sample that we had irradiated for 24 hours showed a maximum increase in the absorbance value, and we can see that set C showed sensitivity for about zero point 0.1 millimolar concentration for perchlorate, and though below this range there isn't linearity in response, but we can sense the presence of perchlorate even up to the nanomolar range. The same analysis showed that as we go on from stable to 15-minute irradiated particle to 24-hour irradiated particle, the particle size decrease. This is due to the energetic radiations which are present during the synthesis, and the presence of perchlorate does not hamper the size distribution of the nanoparticles. The IR spectrum of the perchlorate treated nanoparticles shows the presence of perchlorate in the medium, and we can see that when iron nitrate dissociates, they produce 4 ions. When our iron perchlorate dissociate, they produce 4 ions. But when iron nanoparticles are exposed to perchlorate ions, there is a change from 3 number of ions to 4 number of ions. So this is an entropy driven process, and so it is thermodynamically favorable, and this kind of interaction is favorable. So the main findings here is the polyphenol capped amorphous iron oxide nanoparticles were synthesized using polyphenols, and they were prepared in presence of gamma irradiation, which was found to be more effective in sensing of perchlorate ions, and the method highlights are economically viable for nanoparticle synthesis and opens an avenue for novel analytical applications. Next, we found that block copolymer mediated synthesis of palladium quantum dots were found suitable for the reduction of chromium 6 to chromium 3. So, we synthesized the nanoparticles in presence of non-toxic, um, harmful biocompatible block copolymer PEG, polyethylene glycol, block polypropylene glycol, block polyethylene glycol. Then we characterized and utilized the system for conversion of this toxic chromium 6 to safer chromium 3, and we carried out the reduction in presence of gamma irradiation, which was found to be more effective. The use of quantum dots are normally found in production of catalysts, semiconductors, LEDs, medicines, and so on. And we have checked the critical micellization concentration of this block copolymer and found it to be 0.6% weight by volume. And we have taken 1% block copolymer solution, and to this we have added 1 ml of 1 millimolar palladium salt solution kept in the room temperature for 3 to 5 minutes, which showed transformation of yellow color to brown, which indicated the formation of palladium quantum dots. The characteristic surface plasmon was found to be nearly about 430 nanometer. TEM image showed particles of about 2 to 4 nanometer size, and the SAED pattern shows circular rings which indicated the presence of FCC type crystal lattice. And the DLS showed, dynamic light scattering experiment showed that there were about 300 nanometer size particles. This large difference is due to the presence of long polymer chains around the nanoparticles, which showed reflected a higher hydrodynamic radius. The zeta potential values increased due to the presence of charged palladium uh, quantum dots, which were surrounded by the block copolymers in the solution. Now, chromium 6. Why do we need its reduction? Because chromium 6 is xenotoxic carcinogen. The respiratory tract is the major target organ for chromium 6 toxicity for acute and chronic inhalation exposure. Kidney damage, liver failure, blood cell damage happen due to its oxidation. However, chromium 3 is an essential element to humans. It is essential to normal glucose, protein, and fat metabolism. Body has several systems for reduction of chromium 6 to chromium 3 in blood before entering into the cell. And dietary supplements are chromium 3 picolinate and chromium 3 polynicotinate. So for the reduction, we have taken 1 ml of 1 molar chromium 6 solution and added palladium quantum dot solution to it, and also added 1.75 molar acetic acid. We have observed reduction of chromium 6 at 350 nanometer absorption peak with increase in the acid concentration, as well as with increase in the palladium dot concentration, as well as with the increase in time. So we can see that it is possible to reduce the chromium 6 to chromium 3 only with the palladium quantum dot solution. But the problem is the particles are only 3 to 4 nanometer size. So it is very difficult to regenerate the particles after the reduction. So if we irradiate the solution with gamma radiation, it just throws the particles out from the solution, and we can regenerate the precipitate of palladium nanoparticles and use it for the second cycle and the third cycle. This graph shows that after the reduction of the first cycle and irradiation, we can use gamma irradiation, we can collect it for the second and the third cycles. But there is a problem: we can, though we can reuse, the reaction never goes to completion. So if for the first cycle, that is just after adding the chromium 6 solution to the palladium quantum dot solution, we just irradiate with the first cycle, then the reaction goes to completion with the irradiated solution, as well as we can regenerate the palladium quantum dot for the second and third cycles. So it is always beneficial to irradiate at the first cycle, and irradiation always comes to help. Now, concluding this part, simple one pot method for the synthesis of palladium quantum dots has been designed. No need of special conditions is required. Size of 2 to 3 nanometer, greater surface area, offering application in catalysis of chromium 6 to chromium 3 at room temperature has been obtained. Gamma irradiation causes subsequent precipitation of the catalyst without loss of activity. Palladium quantum dots can more effectively catalyze reduction of chromium 6 to chromium 3 in presence of gamma irradiation. Now this is the last part where I would discuss about the effect of gamma irradiation of ruthenium morine nanocomposite for the trace detection of some lanthanoids, cerium 4, cerium 3 and dysprosium 3. Now, synthesis of ruthenium morine nanocomposite via green process. Then we have characterized using different analytical methods and application towards synthesis of lanthanoids. Now, we have used morine as a capping and reducing agent. We have used water is to ethanol in 1:1 mixture, and morine is available in different food items. And we have chosen the sensing problem of lanthanoids because all the lanthanoids ions have similar ionic radii, and they behave very similarly because of this similarity in their ionic radii, and it is very difficult to differentiate them from one another. So for this, we have prepared ruthenium morine nanocomposite in open atmosphere as well as in presence of gamma irradiation. So we have mixed ruthenium chloride solution and morine solution in 1:1 ratio and adjusted the pH to 12 and kept it for 24 hours. We call it set E. And a similar solution we have prepared and kept it in 24 hours in the gamma irradiation chamber with a dose rate of 1.59 kg per hour, and we call it set B. Then we have characterized the solutions, and we have chosen absorption spectrum spectroscopy for obtaining the top plot and the Benesi-Hildebrand equations. And we can see that the top plot gives the band gap, and we can also see that at pH 12 the band gap is the highest, which means the particle size is the least for pH 12, and the lowest particle size means the surface to volume ratio is the highest for this particular pH, and so the efficacy of sensing would be highest at this pH. The Benesi-Hildebrand plot gives the association constant of the complexation and the ruthenium is to Morin ratio present in the complex. Uh, the emission spectra, because Morin shows fluorescence, we can also obtain the Stern-Bolmer constant, which shows the complexation stability constant or the Stern-Bolmer constant from the fluorescence spectroscopy. Transmission electron microscopy shows particles of nearly 20 to 30 nanometer size. Frail lattice fringes with porosity for both set A and set B can be seen, and fine microcrystallinity can also be observed in both kind of particles. IR spectral pattern shows that in the pure Morin sample there are different kinds of peaks of OH stretching, C double bond C stretching, but the metal CO bond stretching bond frequency near 2000 to 1800 centimeter inverse can be observed in both set A and set B. This is due to the complexation between ruthenium and Morin, and these peaks can be observed in both set A and set B. The particles of the nanocomposite were both found to be amorphous, and the gamma irradiated particles of set B are found to have lesser size from the dynamic light scattering than the non-irradiated sample. This is due to the presence of high energy radiation, which does not allow the particles to agglomerate and grow larger in size. Now for sensing, we have six different lanthanoid ions: lanthanum, cerium-3, cerium-4, samarium-3, gadolinium-3, and dysprosium-3. Three different pH solutions: pH 2, pH 7, and pH 12. Two different nanocomposite solutions, set A and set B. Two different spectroscopic techniques, UV and fluorescence. We observe that only set B is capable of sensing cerium-4, cerium-3, and dysprosium-3 out of 6 lanthanoids, and pH dependent sensing with mutually exclusive conditions. We observed that cerium-4 spectral absorption spectral sensing can be seen at pH 2, at pH 7, and pH 12, whereas at pH 7 emission spectral sensing can be observed, and for dysprosium 2 at pH 2 absorption spectral sensing can be observed, while for cerium 3 at pH 12 absorption spectral sensing can be observed. Neither gamma irradiated Morin nor ruthenium chloride solution alone is capable of sensing of the lanthanoids. Only our Morin complex of ruthenium, and that too in the gamma irradiated condition, is capable of sensing these ions. Now for cerium-4, we can see that the lowest detection limit is 0.09 micromolar at pH 12. For dysprosium 3, the LOD is 5.37 micromolar, and for cerium 3, it is 0.08 micromolar by absorption spectrometry. And the talk plot shows that there is decrease in the band gap value after sensing. The decrease in the band gap value from the initial condition means that the particles have grown in size. That is, these lanthanoids have invaded the complex of the ruthenium Morin and broken the complex and enhanced the size, and that is the reason behind their sensing. And FTIR spectral pattern after sensing, we can see that the peak in the 1800 to 2000 centimeter inverse have disappeared, indicating that the metal Morin, that is ruthenium Morin bond, has disappeared in both the cases. Also in case of cerium 4, we can see the disappearance of the 1943 band. So the plausible mechanism is that due to very high reduction potential value, 1.72 volt of cerium-4, it can easily oxidize ruthenium Morin at all the pH. At very low and high pH of the medium, the excess concentration of proton or OH minus causes a blocking in the emission pathway, thereby breaking the optical environment inactive towards the analyte. Making gamma irradiation cause cleavage of MO bonds and generation of free radicals and active species. Cerium-3 remains as CeOH-4 at pH 12. The high basicity of the species increases the electron density on the irradiated Ru Morin species. Dysprosium 3 at pH 2 carries a very high effective nuclear charge of 8.85, higher than the other ions studied, leading to low ionic radius. At pH 2, the OH moiety of morine gets protonated and remains surrounded by the active free electrons produced by irradiation. The sterically crowded ruthenium morine environment can now be invaded only by the small dysprosium 3 species. Studying the interference, we can see that from the absorption spectroscopy, there were no observable interference for cerium 3 sensing, neither for dysprosium 3 sensing at pH 2. Neither we absorption spectral interference for cerium 3. Only we could observe interference from lanthanum, samarium, and gadolinium for the fluorescence spectral sensing, which is quite obvious because fluorescence spectrum is studied at excited state. We have done the environmental sample analysis for tap water and groundwater and could find appreciable recovery percent in both the cases. So finally, for concluding this work, only the gamma irradiated nanocomposite set B is capable of sensing of cerium 4, cerium 3, and dysprosium 3 at different pH media out of a set of lanthanum 3, cerium 4, cerium 3, samarium 3, gadolinium 3, and dysprosium 3. Cerium 4 can be sensed at pH 2, 7, and 12, whereas cerium 3 can only be sensed at pH 12, and dysprosium 3 can be sensed at pH 2. The limit of detection for sensing of cerium 4, 3, and dysprosium 3 are 0.09, zero point zero 0.08, and 5.37 micromoles, respectively. The absorption and spectrophotometric analysis also suggested that neither the examined transition metals nor the lanthanoids make any significant interference in the analysis. A significant interference was, however, observed from lanthanoids when analyzed fluorimetrically. On analysis of environmental samples, we observed significant recovery of cerium 4, cerium 3, and dysprosium 3 from tap water, and cerium 4 and dysprosium 3 from groundwater at low to neutral pH. So I should thank all my students for their hard work behind the experiments, and I must thank the funding agencies, and thank you all for your kind attention.